Welcome to the sixth lecture of module 5 of this course called Game Theory and Economics. Before we start this lecture, let me take you through what we have been discussing. So in this module and for last couple of lectures, we have been discussing subgame perfect equilibrium, which is also known as subgame perfect Nash equilibrium, which we have seen is a refinement over Nash equilibrium, the idea of Nash equilibrium in the context of games which are extensive games, which means that the actions are taken sequentially and the players are aware of each other's actions which have taken place before they are supposed to take any action. So there is no problem of information. People are aware of the other actions taken by other players. So this is the and we have defined what is a subgame perfect Nash equilibrium. We have said that it is a strategy profile where in each and every subgame there is equilibrium, in the sense that if we define subgame, what is known as a subgame in an extensive game, there will be many subgames. Now the strategy profile should be such that the strategies of the players are optimal given the strategies of other players, and this should happen not only at the beginning of the game but each and every subgame. So that is that, and we have seen that there is another easy way to find out this subgame perfect equilibrium through what is known as backward induction. And this method of backward induction can be used if the game is a finite horizon game, which means that the length of the longest terminal history is finite. In that case, we can go back to the end of the game, look at subgames of length 1, find out what are the optimal actions of the players who are supposed to move at the beginning of those subgames of length 1, and taking those actions as given, we go backwards and try to find out in games of length 2, in subgames of length 2, what are the actions of optimal actions of the players who are supposed to move in the beginning of those subgames, that is subgames of length 2. So likewise we go backwards, going to subgames of length 3, length 4, and going backwards through this induction method, we go to the beginning of the game, and the chain of optimal actions that we get from this process will be the subgame perfect Nash equilibrium or equilibrium, as the case may be. So this is the method of backward induction. What we propose to do today is to discuss some exercises of using this method of backward induction and how to find out the subgame perfect equilibrium through this method. One exercise that we have done in the last lecture, which will be relevant today, was the exercise of synergic relationship. So in that exercise, if you remember, there were two parties, two players basically, and the actions that they were taking were such that if you put more effort, then your output or your payoff will go up, provided that the other player also puts more effort, and this going up of the output also is not a very linear. It does not go up in a linear fashion, but in a non-linear fashion, and the actions are taken by not simultaneously, as it was the case in a strategic game, but sequentially. So first player 1 moves and chooses A1, and then player 2 moves and chooses A2, and then the game ends and the players get their payoffs. So in this case, what we had is that The actions were the set of actions, it was not a finite set. There could be infinite number of actions a particular player can take. It was a continuous variable. The action was a continuous variable, and in that problem what we applied, this method of backward induction, we tried to go back to the end of the game. At the end of the game, it is player 2 who is supposed to move. We look at her optimal action, that is A2 given A1, and which is nothing but the best response function of player 2 given A1. So A2 is a function of A1. Now this A2 as a function of A1 now will be used by player 1 to find out what is his optimal action in the first stage. So in this case, player 1 is basically second guessing player 2 and taking a preemptive action such that his payoff becomes more than what could have been the case had they taken their actions simultaneously. So this is one important conclusion that we derived in the last lecture. Today we shall start with one exercise which is similar in spirit to that synergic relationship example, and this is called the problem of labor union and firm. So let me first read out the exercise and then we shall try to solve this. There is bargaining between the labor union and a firm which employs labor. The union has the payoff function U as a function of W and L, an increasing function of both wage rate W and the total labor employment L. The firm has the profit function pi, which is equal to RL minus WL. RL is the revenue. It is an increasing but concave function of L. So if L rises, so total employment of labor, if it rises, it increases the utility or the payoff of the union because more of its members are getting employment. If more labor is employed, what happens to firm's profit? It rises, but not in a linear fashion. It rises in a declining fashion because the reason is that if you employ more and more labor, the productivity of the additional labor units goes on falling. So the first labor might be adding a lot to your output, but the 100 first unit of labor might not be contributing that much to your output, and that is why your output will not rise that much, therefore your revenue will not rise that much. So that is the effect on revenue. And if I look at the profit function of the firm, revenue is not the only thing that I should consider. I should also consider the cost. If more labor is employed, there is more labor cost. So unequivocally, if labor rises, L rises, cost rises, and we have assumed that this relationship is a linear relationship, W multiplied by L. So this is what the union wants to maximize U, and this is what the firm wants to maximize. And there are two variables here, one is W and the other is L. Now how is the bargaining taking place? In stage 1, the union proposes a wage rate W to the firm. In stage 2, the firm decides how much labor to hire. Solve the subgame perfect equilibrium of the game through backward induction. So this is the exercise. There are two stages to this game. In stage 1, the union says, okay, we want this wage rate, this W for 1 unit of labor that you will employ, and after the union tells its W which it wants to have from the firm decides how much labor it will employ. And so W and L are decided, and then the two parties, two players get their payoffs. We have to decide which is the subgame perfect equilibrium through the method of backward induction. Now, why did I say that this exercise is relevant to the synergic relationship exercise? Because here there are many similarities. First, there are two parties involved and there are two stages. The union, let us call it U, is like the first player. And here comes the second similarity. The variable that it is deciding, which is W, is a continuous variable, like it was A1 in that synergic relationship exercise, which is also continuous. W can presumably take any positive, it can take 0 also hypothetically, any non-negative value, and then, so that is why I have this continuous range here for W, and after it has decided W, then the firm moves in and decides how much labor it will employ, which is L. Okay. Again and again, L is a continuous variable, it can take any value between 0 and infinity. After W and L have been decided, the two parties, that is the union and the firm, get their payoffs, and these are the payoffs. So, this is where the game ends, and we have to figure out how to find out the subgame perfect equilibrium. Now, as before, what we shall do is that we shall start with subgame of length 1, which is this subgame, find out the optimal action of the firm and go backward and try to see what is the optimal action by the union if the firm has taken its final optimal action. Now, to go into that, before we go into that, let us look at the nature of these payoff functions. First, let us look at U. This is the payoff function of the union. We know the following. That the payoff is increasing both in wage rate and the labor employment. If wage rate W rises, utility rises. If L rises, again payoff rises. So, this can be represented by a downward sloping line like this. This line or this line, these are called indifference curves. So, the idea is that along any of these curves, there could be infinite number of such curves which are parallel to each other. Along any such curve, the payoff of the union remains constant. So, that is why we are calling them the indifference curves. Union is indifferent between 2 points on the same curve. And we have assumed that the curves are convex to the axis, but this does not necessarily follow from the utility function and the assumptions that are given. So, the implicit assumption behind the convexity of the curves is that the second derivatives, that is del square u del w square and del square u del L square, they are negative. So, the utility margin, what is called the marginal utility of wage rate and L are positive, but they are diminishing, and therefore, we have this convex indifference curves. And what does a union want to do? Any union wants to maximize the utility. So, it wants to go as far as possible away from the origin. So, it wants to reach as high an indifference curve as possible. The high indifference curves are to the northeast, more and more towards the northeast of this plane of LW. So, this is what the union wants to do. And what does the firm want to do? Firm wants to maximize this pi, and pi is given by this, and we have this relationship between L and R that the first derivative is positive, which means that if more labor is employed, revenue rises, but it rises at a declining rate, because if you remember, the firm has a profit function pi, the revenue is an increasing and concave function of L. Concave function of L means that its slope goes on declining, which means that the second derivative is negative. So, diagrammatically it will look like the following. So, these could be different R curves for different parameters. In particular, in general, R could be function of not only L but other parameters also. So, I can have many R curves, but since in this particular example no other parameter is given, let us suppose this is the only revenue curve that I am concerned with. Now, what the firm wants to maximize is not this R, but R minus WL. So, one can draw a WL curve also. This will be a straight line, a linear function of L. W is constant in this diagram. So, it is an upward rising straight line going through the origin. What the firm wants to maximize is the difference between these two. So, this area, the difference, the gap is what the firm wants to maximize, and we shall see how the firm wants to maximize. Now, talking about this R and WL, I can also find out what is the indifference curve of the firm, which means along what W and L the firm is getting the same amount of profit. That will not be called an indifference curve per se, but it will be called an iso profit curve. Iso means same. So, along an iso profit curve of a firm, the profit of the firm remains the same, like the payoff of the union was remaining the same in an indifference curve. So, if I want to draw the iso profit curve of the firm, then along the horizontal axis I am having L, but notice along the vertical axis I am not having R, but I am having W. So, this is W, like it is here. W is along the vertical axis in the indifference curve also. So, I want to find out along what combinations of W and L is the firm indifferent. So, those curves will be the isoprofit curves, and I have this function of profit, this. Now, to figure this out, I have this assumptions which are given, that RL is an increasing and declining function of, increasing but concave function of L. So, there are two ways to find out the shape of the isoprofit curves. First is to look at technically what will be the slope of the isoprofit curve at any combination of W and L. For that, what I do is to take the total derivative of this function and set that equal to 0, because along any isoprofit curve the profit remains the same. And from this, what I get is the following. This is what I get by taking the total derivative equal to 0. So, it is R prime L minus W divided by L. This is the slope of the isoprofit curve at any combination of W and L. And how will this behave over if I take different combination of L and W? If I take very small value of L, then I know R prime is high, right, because R prime as such is positive, but it goes on falling. So, if the L value of L is very low, the value of R prime will be high. If I take high value of L, this R prime will go on declining. Now, if R prime L is high, then R prime L minus W, it will be positive, because I can take L as small as possible, so that R prime L eventually becomes higher than W. So, in this case, the slope of the isoprofit curve will be positive. So, it will be an increasing function like this, but as L goes on rising, R prime L will go on declining, right, and eventually a situation will come where R prime L at a particular L, it will happen definitely that R prime L is equal to W, and if R prime L is equal to W, the slope becomes 0, and you can figure out if L rises further, the slope becomes negative, because then W becomes higher than R prime L. So, I have a declining part of this isoprofit curve. So, this is how the isoprofit curve of the firm looks like, and there will be plenty of such isoprofit curves. Each represents a different level of profit. How do I know which curve represents a higher level of profit? If I go on taking more and more curves which are to the north, so I go upwards, then what is happening is that at a given level of L, for example, I can imagine a given level of L, W is rising, which means wage rate is rising. And I know from this profit function that if wage rises, the profit definitely falls given L, given a constant level of L. So, the isoprofit curves which lie to the northerly direction, they represents a lower level of profit, whereas if I take curves to the south or which are closer to the L axis, those isoprofit curves represent a higher level of profit. So, this is how the situation looks like, the isoprofit curves of the firm looks like. Now, what is optimal for the firm? Let us come back to the original question. The original question was, in this subgame, what is the best the firm can do to maximize the profit? So, maximize pi, which is a function of L and W. Now, what is the variable on which the firm has control? It is L. W is something which has been decided by the union in the first stage. So, on W the firm does not have any control. So, W is a parameter for the firm, it is given from outside. And if you have a function which is a function of just one variable, which is L here, and you want to maximize the function, then we depend on the first order condition. Right, here W is given, W is parameter. So, set it equal to 0. So, applying this FOC or first order condition to this particular function, I get the following condition, that L is a function of W. Let us call this f of W. So, this L as a function of W, this f function is the function which optimizes the profit of the firm in second stage given the W which has been decided by the union in the first stage. So, this is the solution from the subgame of length 1. This can be also represented by this diagram. This diagram is something which you have seen before. I'm sorry, this is R. So, you have this rising R function and you have this WL. Now, if W is given, what is the level of L which is maximizing R minus WL? It is given by this tangency point, where the slope of the R function, which is R prime, is equal to the slope of this line, which is nothing but W. So, this is the point. Okay, this is FL, sorry, FW. Given W, this is the level of L which maximizes the profit of the firm. What is the reflection of this analysis, this exercise, this FW in terms of this isoprofit curve? It will look like the following. Remember, there are plenty of isoprofit curves. Now, what this is saying that L is a function of W. At any given level of W, what is the L that maximizes the profit? Basically, this is the L that maximizes the profit. Any firm will like to have or like to reach that isoprofit curve which is closest to the L axis. Now, if it chooses a point like this, the corresponding isoprofit curve is this, which is a lower level of profit. Here also the profit is even, this point represents a even lower profit. So, this is the point where the profit is maximum. So, if I have different levels of W, I am essentially getting different levels of optimal L, and this is the line that connects all these optimal L's, and this is the line which is nothing but FW. Here f as a function of W, it is just the other way around. Basically, W is the independent variable here, whereas that independent variable is represented along the y axis. So, FW is the decision of the firm given a value of W. Now, we shall go backwards and try to find out what is the optimal action by the union. So, in subgames of length 2, and there is just one subgame of length 2, that is after history phi, the union has to decide, the union maximizes U, which is a function of L and W, but keeping in mind what? The optimal action of the firm in stage 2. By taking L is equal to FW as given. Okay. So, the idea is to maximize, and what is the decision variable here? It is W is the decision variable. So, W is the thing that is the union is deciding, and by manipulating W it wants to maximize this. So, and what is the additional information that I have is that L here is a function of W itself. So, this is just a function of one variable, and the union wants to maximize that function with respect to that variable. So, therefore, we shall get from first order condition right. Just differentiating this function with respect to W and set that equal to 0, and that will solve for W star. So, this is how it is done. First, L is expressed as a function of W, then that relationship is taken by the union and used to maximize its own utility. So, in terms of, this is the thing in terms of mathematics, but diagrammatically how does it look? So, we had different indifference curves for the firm, downward sloping convex indifference curves, and we also had this relationship which is known as the F as a function of W. So, what is the W in terms of this diagram, which is W star, which is the optimal for the firm? Well, this relationship FW is given, and it is taken as given by the union. because it is decided by the firm. Now, taking this as given, the firm wants to maximize its utility, and remember the indifference curve which are to the northeast represents higher level of utility, and therefore it wants to touch, the union wants to reach or touch as high an indifference curve as possible, and again this is going to happen at the point of tangency. So, therefore, this is my W star, and given this F, I have got this L star, which is basically the L which the firm will decide in the next period. So, this is the solution. One interesting property of this solution is that this solution is not an efficient solution. From this equilibrium, this W star and L star, which is a subgame perfect Nash equilibrium, one can reach a better equilibrium, more efficient equilibrium, and this I shall show by diagrams. Let me draw a different diagram so that the picture is not cluttered. This is suppose the f function, and this is the tangency point. It does not look like the tangency point, but suppose this is the tangency point. So, therefore, since this is the tangency point, this is W star, this is L star, this is the equilibrium. If on the same diagram I want to superimpose the isoprofit curves of the firm, then how will it look like? I know that along this f function, the firms are having their maximum points of the isoprofit curves. Look at this. The highest points on the isoprofit curves, they lie on this line, the FW line. So, it will be the following, this, right, and here is the problem. This is the equilibrium. So, in the equilibrium, what is the level of utility obtained by the firm? Let us call this U star, which is represented by this indifference curve. And what is the profit that is obtained by the firm? It is represented by this isoprofit curve. So, let us call this pi star. The point is that both the union and the firm could reach better levels or more improved levels, higher levels of U and pi than this equilibrium of U star and pi star. How do I know this? Look at this lens, this shaded region. If I take any point in this shaded region, let us take this point here. This is a point. Now, in this point, the characteristic of this point is that it is on pi star. So, the profit of the firm is same as in W star L star. But at this point, the firm, the union is having a higher level of utility, because this is U dashed, which is a higher level of utility than U star. And this kind of improvement of one person's utility, one player's utility, keeping the utility of the other player constant, is possible for many such points in this shaded region. In fact, it is possible to take some point inside where both the firm's profit goes up and the union's utility also goes up. So, that is why I am saying this W star and L star is inefficient, though it is subgame perfect equilibrium. So, this is just a comment that subgame perfect equilibrium may be inefficient. So, this was one exercise. Let me take another interesting exercise which again uses the idea of backward induction. This is the centipede game. So, here you have two players, there are two players, players 1 and 2. Each player starts with 1 rupee. They alternate saying stop or continue starting with player 1. So, player 1 is the first mover, it either says stop or continue. When a player says continue, 1 rupee is taken away by the referee from his pile and 2 rupees are put in the other player's pile. So, in first stage, if player 1 says continue, then his 1 rupee which he started with, because he is starting with 1 rupee, that will be taken away from him. So, he will be left with 0 rupee, and the other player, the second player, will be given 2 rupees. So, the second player will be getting in all 3 rupees in the second stage. As soon as either player says stop, the game is terminated and each player receives the money currently in her pile. So, if in the second stage player 2 says stop and does not say continue, then player 2 will get all those 3 rupees and player 1 will be left with 0 rupees. Alternatively, the game stops if both players' piles reach 100 rupees. So, this way the game continues. If in stage 2 player 2 does not say stop but says continue, then 1 rupee will be taken from him and 2 rupees will be given to player 1. So, in the third stage player 2 will be getting will be left with 2 rupees and player 1 will be left with 2 rupees, and then it is up to player 1 to continue or not to continue. If he says continue, again 1 rupee will be deducted from his pile and 2 rupee will be given to player 2, like that. Why does the game end? If everyone continues to say continue, then the game stops if both players' piles reach 100 rupees. So, once both the players are getting 100 rupees each, the game is stopping there. What is or are the subgame perfect equilibrium or equilibria of the game? So, this is a game of perfect information. And let us see what could be said about the subgame perfect equilibria of this game if we apply the idea of backward induction. First, try to draw the game tree of this centipede game. So, I know the starting point is player 1 and player 1 can say stop, S is stop and C is continue. And it can say continue. If it continues, the game reaches player 2. If stop is the decision by player 1, the game ends there, it is terminated there. Player 2 again can say stop, again the game ends here. It can say continue, the game progresses. Then again it is player 1's turn to move, stop and continue. So, that is the way it moves on, and you can see why it is called the centipede game. Why does it end? It ends somewhere here, where 100 rupees is by each of the players is reached. Now, who is the last player that moves and therefore the piles reach 100 rupees? Something we can know if we look at this pattern of the payoffs. So, let us look at the pattern of the payoffs. In stage 1, if player 1 says stop, then there is no game, there is no progress of the game, and the initial endowment of 1-1 is the payoff that they are getting. If player 1 says continue, then obviously 1 rupee will be deducted from his pile, and player 2, if he says stop now, then he will get this 2 rupees and player 1 will be left with 0. Instead, if player 2 says continue and in the next stage player 1 says stop, then basically 1 rupee had been taken away from player 2 and this is transformed into 2 rupees and given to player 1. So, this is what the payoff after stage 3. If player 1 says stop, says continue, again 1 rupee will be taken away from him, and if player 2 says continue in the stop in the next stage, 1-4 will be the payoff. So, likewise it goes on. The question is, how does the game look like in the termination point? One thing is important is that when the payoffs are equal, that is 100-100, that is a decision taken by player 2. See, here 2-2 is happening, and this was the payoff which was taken by player 2. He said continue, and that is why it became 2-2. Likewise, here also player 2, if he says continue, then only, and if player 1 says stop, the game stops here, then only it becomes 3-3, right. So, the last decision must be by player 2. And what about the so this is, he said continue, that is why it became 100-100. If he had said stop, then what would have happened? That can also be figured out. If he had stopped the game before that, it would have been 98-101, because 1 rupee will be taken from him. So, 100 from 101 it becomes 100, and 2 rupees will be added to player 1's pile. So, that is why it becomes 100 from 98. So, if I look a little backwards, then this is C, this is 1, this is S, and it will be 99-99, sorry. Right, because 1 is saying continue, if he had not said continue, and if he had said stop, it would have been 99-99, because from 99 1 rupee is taken from player 1's pile, so it becomes 98, and 2 rupees are added to player 2's pile, that is why from 99 it becomes 101. So, this way there is a gap between these two ends. This way the game looks, and you can see it looks like a centipede. Now, what is subgame perfect equilibrium here? Interestingly, here there is a unique subgame perfect equilibrium, and that is saying stop at each subgame, and for both the players. Why is this so? Because again I can go back at the end of the game. At the end of the game, player 2 has to choose between 101 and 100, and definitely he will stop at 101, which is more than 100. And given that player 2 is going to stop at 101, which gives player 1 98, there is no reason for player 1 to continue at this stage, because he is getting 99 here. So, why should he pass on the game to player 2 where he will get 98. So, the same reasoning basically takes us back, and basically it means that the game ends here itself, which means the terminal history is this. S. So, this is the terminal history, and payoff, equilibrium payoff, is obviously 1 1. So, this is again one important and interesting result that we are getting, that the subgame perfect equilibrium could be very inefficient. This game, if they had trusted on each other, they could have got 100 each, and which is much better than 1 1. So, because the players are thinking that the other players are rational, and depending on the rationality of the other person, therefore, gives them a payoff which is much suboptimal than what they could get at 100. Let me take another exercise and then we shall close this lecture. This is the exercise of heterogeneous objects. Let me just describe the game, maybe we will not have time to finish this exercise. Two people choose k which is greater than two objects in turn. First, player 1 picks up an object, then player 2 picks up one. In the third round, player 1 gets to move, etc. Preferences of the players are different. No player is indifferent between any two objects. Each player evaluates a set of objects according to the sum of the values she assigns to the objects in the set. Let xk denotes the object least liked by the player who does not choose the object in stage k. Let xk minus 1 denotes the object among the objects except xk least preferred by the player who does not choose in the stage k minus 1. This way we can denote all the k objects by x's. Show that there may not be any subgame perfect equilibrium in which player 1 chooses her favorite object in the first round for k is equal to 3. Also show that if k is equal to 3, the game has a subgame perfect equilibrium in which for each j going from 1 to k, the object xj is chosen in stage j. So, it is quite a long question. Let me try to do the first part of the exercise, which is the following, that there are two players, suppose there are 1 and 2, their preferences are different. Now, what we have to show is that there could be preference patterns in this for these two players such that player 1 will never pick up his favorite object in the first round. These two players are picking up their choices, their objects from a set of 3 objects. So, 3 objects are there. In first round, player 1 picks her object. Now, this object may not be her favorite, and that is what we have to show. And in second round, player 2 picks up her object, and in the third round, player 1 again picks up her object, and then the game terminates because there are only 3 objects. What we need to show is that in subgame perfect equilibrium, it can happen that player 1 does not pick up her most favorite object in the first round, and that is what we want to show in the next lecture. And that there is also the exercise that it will, if I define these 3 objects in terms of x1 and x2 and x3 in a particular way, which we shall discuss in the next lecture, then x1 will be chosen in the first round, x2 will be chosen in the second round, and x3 will be chosen in the third round. So that is where we shall begin in the next lecture. Thank you. This is called the rotten kid problem. This is a game between a child and her parents. First, the child takes an action A, which produces income for the child, denoted by ICA, and income for the parents, IPA. Then parents choose a bequest B for the child. Child's payoff is U IC plus B, because this is the total income, and parents payoff is something more complicated. It is V of IP minus B plus K multiplied by U of IC plus B, where K is greater than 0. Okay. A is a non-negative number. Income functions IC and IP are increasing concave functions maximized at AC and AP. Utility functions are strictly concave and increasing, proved by backward induction that the child maximizes family's aggregate income IC plus IP, although she is not altruistic. So, let us first briefly in terms of notation describe the game. First move is made by the child, and the variable that she chooses, it is a continuous variable, it is called A. Once A is chosen, that A is determining two things. One is called IC, the income of the child, which is a function of A, and IP, the income of the parents, which is also a function of A. Okay. So, after incomes have been decided, then the parents, here are the parents, they make a move. So, the parents are here, and the variable that they choose is called B. B is the bequest. And once the bequest, what is the bequest? Bequest is the money that the parents are leaving for the child, that is capital B. Once the bequest has been decided, what is the income of the child then? Income of the child becomes IC plus B. So, then we talk about the utility, that is the payoff of the child, which is given by capital U IC, which is a function of A plus B, all right, and the payoff of the parents, which is in fact a composition of two things. One is V, which is IP, which is a function of A, minus B plus small k multiplied by U, which is the utility of the child. Okay. So, this is the game. Just before trying to solve the game, what is happening is that the child is determining the income of both the child and the parents, and the parents then are giving away some money from their income to the child. Now, the child is not altruistic. We can see that his payoff is a function of his own income. It does not depend on the utility, that is the satisfaction of the parents. Whereas the parents' payoff is their own payoff, okay, the individual payoff plus k is positive, multiplied by the payoff of the child. So, if the child is getting more payoff, that satisfies the parents because k is positive. So, the parents are altruistic, but the child is not. What we have to show that even in this case, the child is going to maximize not his individual income, not IC, but IC plus IP. That is the income of the combined income of the child and the parents. Okay, so we have to use backward induction here. So let us look at subgame of length 1. So we are talking about the subgame following A. In this subgame, the parents are maximizing their payoff. So they are maximizing this function. With respect to B. B is the variable that they have control over. So from first order condition, we shall have V prime, sorry, this should be minus. Okay, this is minus because V prime minus multiplied by minus 1 plus K of Q prime multiplied by plus 1 is equal to 0, which means that V prime, which is a function of IP minus B, plus K multiplied by U prime, which is a function of IC plus B, is equal to 0. Now we are going to manipulate this relation a little bit. We are going to take partial derivative with respect to A. And if we do that, we get the following. After some manipulation, we get this relation. It is V prime IP dash minus K U double prime IC dash divided by V prime plus K U double prime. Now this is what is known by the child, that the parents are maximizing their payoff here, and now taking that into account, the child is going to maximize his payoff. So child after history 5 maximizes U IC plus B with respect to A. So what we get is the following. This is the first order condition, and then we use 1, and using 1 we get the following. After some manipulation, I am jumping the steps. IC dash plus IP dash is equal to 0, which means that IC plus IP is maximized with respect to A, hence the proof. Okay, thank you.